Hello, this is Lab 4 called Oscillations, in which we determine the motion of the spring mass system as it moves in a trajectory arc. The purpose is left to record and analyze the motion of the spring mass as it oscillates on the spring, moves circuit in the arc to determine the object position using a tracker, and then create a computation model based on Newton's second law and compare the data from the computation model to the observed data corresponding to the x, y position and time of the object oscillation. In the summary of the lab, the motion of the object is very similar to the computation model in both the x and y direction, except for a few differences due to the force of drag. As we mentioned in previous labs, Newton's second law showcased the relationship between acceleration, velocity, and time, and states that the motion of the object is dependent upon the net force and the mass of the object. Two variations of the formula is velocity update formula and the position update formula, as well as F net equals mass times change of velocity over change of time. The gravitational force is equal to negative mass times gravity. Hooke's law, also known as spring force, is equivalent to the K constant times the relaxed length minus the regular length. And the period of oscillation is equivalent to the K constant equals 4 pi squared times mass over period squared. The energy principle represents the work done by an object within a system and is equivalent to the change of energy within a system. And the total energy is equivalent to the change in kinetic energy plus the change in potential energy. The calculations for the lab is shown here. Here we have the mass of the solid, the initial position of the mass, the final observed time, and the mark frame. We calculated the period of time to be 1.519 seconds, and then determined the spring stiffness with the following formula, getting a value of 6.87 newtons per meters. We determined the final length of the spring to be 0.70 meters, and the regular length of the spring to be 0.126 meters after the calculation. Within Tracker, the coordinate plane was centered at the center of the fixed attachment point labeled within the analyzed video. The motion of the ball's oscillating motion was in the x and y direction. The length between the attachment point and the center of mass is 0.70 meters and was set as the length reference within the Tracker application. This slide represents the motion of the tracker as the object was oscillating. As you can see, I set the points of the center of mass as shown by the red diamonds, and you can see the motion moving in the x and y direction. The frame was trimmed to begin at the exact moment the ball is let go, and the motion of the object is not exact due to drag force, but that will be explained later on. This is the composition model that I'll be comparing with my tracker data. To begin, I stated the mass of the object as stated before, the initial position, the initial velocity, and the gravitational constant, which is 9.8 meters per second squared. I stated the calculated spring stiffness, the relaxed length of the spring, the strength of the spring, which is calculated by taking the ball position minus the spring position, and then applying the direction and the length between the regular and relaxed length. I did determine the kinetic energy, which is 1/2 ball times magnitude times ball velocity squared, the gravitational potential energy, the spring potential energy, and the total energy. At the start of the time loop where the time represents the last observed time point, I first set the initial energy equivalent to the original value, and then state the gravitational force, which is negative mass times gravity. I calculated the force of spring as shown here, and then calculated the total net force to be gravitational force plus spring force. I then used Newton's second law to update the object's velocity and the object's position, and then updated the stretch of the spring through application of the new mass position as shown here, where L is equal to ball position minus spring position, and L hat equal to L divided by magnitude of L. I then incorporated the change in energy within the system, as shown here, where the total energy is equal to 0. This is a simulation of the computational model after my code is finished and ran. As shown here, you can see the spring oscillating in both the y direction and the x direction. And you can see the change in energy in the graph shown below here. This slide shows my position versus time graph, where the graph on the top represents the oscillation of the mass on the x direction, and the graph on the bottom represents the oscillation of mass in the y direction. The red curve represents the tracker experimental analysis, while the blue curve represents the computation model. The computation model and the experimental model are extremely similar, as the motion displayed within the computation model in the x-axis is slightly faster than the motion within the experimental model. The experimental model in the y direction is much more drastic compared to the computation model, showcasing the effect of other forces in the real world. The reasons for the discrepancies within my motion is that the competition model did not take into account drag force, which may cause resistance within the motion of the object as it is swinging. In addition, there may have been an error within the tracking point when determining the center of the mass in each time frame when using tracker. Is the energy principle satisfied? This graph showcases the change in energy within the oscillation of mass in the x and y direction, where the blue represents kinetic energy, the red represents gravitational potential energy, the green curve represents spring potential energy, and the orange curve represents the total change in energy, which is zero. The energy principle is satisfied within the experiment as the total change in energy is zero, as shown by the orange line, meaning the amplitude of the change of energy within the system cancels out and is conserved, making the total energy remain zero throughout the whole oscillation. There are no surrounding forces on the system to make the change in energy non-zero. This slide shows the oscillation period of the x position and compared to the y position. The period of the oscillation in the x position is 1.614 seconds, while the period of the oscillation in the y direction is 1.519 seconds. The periods of the two data plots are different as it takes longer for the mass to accelerate in the x direction than the y direction. The motion in the y direction was used to predict the ball oscillating in the spring, and the two periods will each have two different Ks values and spring forces due to correlation, and the x position will have a smaller Ks value than the y value.